going to start this video with a throwback. A couple of weeks ago I asked you to do a revision poster on 4.14 and 4.15. So, as you did it, answer this question. A coherent laser beam is incident on double slits. Sketch the pattern that you would see on the screen. What wave behaviour causes it, and what does it tell me about the gap size? Imagine you could somehow do this in 2D, right? Imagine that your double slits were actually like a circle of slits. Don't worry about the practicality of how that would happen, but rather than having two lines, you shone the light through like a circle. Perhaps even maybe if you diffracted it around something that was very small. What do you think that would look like? Now, I use the word rotational symmetry here. So if we gave our two slits rotational symmetry, we should give the pattern, the fringe pattern, rotational symmetry as well. Basically means it goes from being a straight line to being a circular pattern. We still see a central bright fringe, and then we see other fringes coming out from the centre as well. Why are you asking me this, Rob? Could they ask it in an exam? No. I'm actually asking you this because it's relevant to what we're going to have a look at today. Keep this diffraction pattern in mind, because today we're going to have a look at a weird effect that you might not have thought would ever happen before. Diffraction is evidenced for the wave model of light. Particles don't diffract. But would it break if both models are true? Would the world break? Well, no, because both models are true. We can see the photoelectric effect happens, we can make solar panels, but we also see diffraction. Light can behave both as a wave and as a particle, depending on the circumstances. And it is perfectly allowed to do that. It's called wave-particle duality. It's something that happens everywhere. I'm of the school of physics that just says, deal with it. You might have heard about that on popular science shows or in the media, and they blow it up to be this crazy thing. That's how science communication works in the world that we live in. I disagree with it. Wave-particle duality is not special. It's something that happens everywhere. What's really interesting is when we go in to actually understand it and when we realise how it works. We know that light can reflect, refract, diffract, it can be polarised, we know it interacts one-to-one as photons with electrons. All of those facts are true. Light can behave both as a wave and as a particle. Would it be that weird then if things that we know as particles sometimes behave as waves? Could we get other particles to behave in the same way as photons? Well, let's have a look. Now, normally I would do this experiment, I miss it so much. You can get a big cathode ray tube. This is part of a standard answer and you kind of need to explain what's going on. A cathode ray tube has a negatively charged plate at one end, something with lots of electrons sat on it. That's called a cathode. That's what cathode means. It has a positively charged plate at the other end. So the electrons on the cathode they're attracted towards this positive plate. They accelerate through that space, but we trick them. In the middle of the positively charged plate, we've put a hole, so some of the electrons whiz towards the positive plate, but then pass through the hole. Poor things. Those electrons that pass through the hole are now going really fast, because electrons do move very fast. And so if I put a tiny sheet of graphite film in front of that anode, in front of that area where they're moving really fast, those electrons will whiz through the anode, whiz through the graphite film, and reach a screen, because we want to see what's going on. So we put a screen in front of it. This is actually how old TVs used to work as well, before they were all plasma screen. But I think you guys were actually not alive when cathode ray TVs were invented, and that really scares me because I had about 3 when I was young. Anyway. On the front of the cathode ray tube, there's a coating that just converts our electrons into photons so that we can see where the electrons are. We use phosphor, but it doesn't matter really, you just need to know that we can then see it. So dead easy system, cathode, accelerate to an anode, which has a hole in it, and they go through the hole, through some graphite film. Think about what you remember from GCSE chemistry and graphite. Graphite is just single atoms of carbon arranged in a hexagonal shape. So some of them might interact with those atoms. Think to yourself before I move on, what should that look like? What we actually see when we do this experiment is on the phosphor screen, we see that diffraction pattern. Again, we see it as a circle. So what must the electrons be doing? The electrons are diffracting around the atoms in the carbon. And this behaviour, electron diffraction, is key evidence for the theory of wave-particle duality. The fact that not only can light waves behave as particles called photons, but actually many of our well-known particles can behave as waves as well. You must be able to state electron diffraction as key evidence for the wave nature of particles. How does a particle gain a wavelength? Under what circumstances do particles behave as waves? This book covers the De-Broglie Wavelength equation. I know it looks like De-Broglie, but he was French. Call him De Broglie and people will be impressed that you're a posh physicist. Call him De-Broglie and they'll know that you're from the northwest. The De Broglie equation is dead easy. It assigns a wavelength to a particle given its momentum. So the wavelength of a particle is inversely proportional to the momentum of that particle. Lambda equals h, Planck's constant, 6.63 times 10 to minus 34, divided by the momentum of the particle. Remember, momentum, p, is mass times velocity. So you might write this, some people prefer to write it as lambda equals h divided by mv. Both of those things are fine. Fill in the blanks, fill in the tasks, fill in the summary sheet. The De Broglie wavelength equation is really easy to use. It's just maths. Can you see why when I started the physics course, remember back in like September and October, and you were worrying about rearranging equations and stuff, I was like, guys, the maths is the easy part of physics, because it really is. The hard part of physics is being able to explain what's going on. Looking at the De Broglie wavelength equation, remember that h, Planck's constant, is the smallest number you will ever experience in physics. 6.63 times 10 to the minus 34. What does that mean for the wavelength? If I wanted the wavelength to be 1 metre, what would the momentum of my particle have to be? The De Broglie equation, because h is so small, we want p to be as small as possible to get lambda as large as possible. So for example, there's that task in the book that says calculate the De Broglie wavelength of a cricket ball travelling at whatever speed. If you look at the wavelength that's calculated, it is absolutely tiny. And that means that it probably does not exhibit wave-like behaviour. It's an unrealistic, it's absolutely tiny. Why can I not behave as a wave? Well, if I weigh 70 kilos and I'm moving at 10 metres per second, my momentum is 700. Planck's constant divided by 700 is times 10 to the minus 36. My De Broglie wavelength would be ridiculously tiny, and therefore I would not exhibit wave-like properties. However, let's think about our electrons. The mass of an electron is 9 times 10 to the minus 31. 10 to the minus 31, that's quite close to 10 to the minus 34. So Planck's constant and the momentum of my electron would be quite similar, and so you'd probably get a wavelength of maybe a few millimeters, maybe a few micrometers, and then you'd start to see, it's behaving like some of our EM radiation. If I had a wavelength of 10 to the minus 9 meters for an electron travelling at a few kilometers per second, that would be exactly the same in terms of diffraction behaviour as having light of a few hundred nanometers. And that is why this is really significant. Small particles with low mass can behave as waves. The De-Broglie equation just tells us what that wavelength is. So I'll just finish by comparing the evidence for wave-particle duality. Evidence for the wave behaviour of electrons, that's what we've been looking at today. It's electron diffraction. So when I shine them through that graphite film, I get that diffraction pattern, which can only be explained using a wave behaviour. You cannot explain why using mechanics, even using statistical mechanics. It does not make sense. It has to be waves. They have to interfere, superpose, and form that pattern on the screen. Happens, of course, when the De-Broglie wavelength is similar to the gap size. Obviously though, for the rest of our scientific career up until now, we've been looking at electrons as point particles, tiny little things. They've got 1/2000th the mass of a proton, they whiz around in atoms. They are, and how do we know this? Well, they can be deflected by fields and stuff, so they interact with other point charges, and those interactions are governed by the rules of mechanics. You'll see in electric fields at the start of Module 6 that electrons obey mechanics laws as well, conservation of momentum, Suvat equations, so they're point particles there. They can be deflected by fields, but I think most importantly, unlike waves, they possess mass, they possess charge. Waves don't possess mass or charge, no known type of wave, so from gravitational to EM to sound, waves should not carry mass. Waves should not have charge. They don't. They're just oscillations. That's all a wave is. So this is evidence that electrons are particles because they do possess those properties. They have a mass, they have a charge, they interact with other particles, they follow the laws of mechanics. Learn this standard answer, you need to know the evidence for wave-particle duality, because like everything that we need to follow in this world, it needs to be evidence-based. The rest of the standard answers just explain electron diffraction, which is something you must be able to understand. I know the diagram might look a bit intimidating, but picture that one from my slide. Cathode is where the electrons come from. Too many electrons, it's negative. Electrons are attracted to the anode, positive. We put a hole in the middle of the anode, they fly through that hole across the graphite and hit the screen, showing that diffraction pattern. Once you know it, it's easy to remember. With the end of this book, 4.18, also comes the end of Module 4. We've finished all of the regular Year 12 physics content. Every other year we'd finish Unit 4 around this time, give or take a couple of weeks. Last year I think we finished it in the week after this half-term holiday. So we're bang on schedule at the moment. What I worry is that the whole of waves and wave-particle duality you will have done at home, and whilst that's fine because you guys are great at learning stuff, I just don't want you to be cutting corners. Because if you're cutting corners now, and I mean this, because every year Year 13s have their wobbly moments because they're trying to catch up on things. I worry that if you've been cutting corners now, it might come back to bite you next year. And that's all, I'm just saying, it might not, but it probably will. I want you to take some serious time over the holidays to do some revision. Produce a further revision poster for wave-particle duality. That's everything from photons to 4.18. Everything on that poster. That way, you know mechanics, it's easy. You've got your 2 posters on electronics, basics, advanced concepts, your 2 posters on waves, basics, advanced ideas, and your final poster on wave-particle duality. It will be a really nice summary of Module 4, and it will save you a lot of work when you come back to revise it for our November exam when we come back. I'm looking ahead to year 13. You guys will come back in September, you have 6 weeks on, and then we run a big sports hall exam. And I think it's really good because it reminds you just how serious this game is. Hopefully it reminds you that we only ever want you to succeed in it. It might seem like hard work right now, but it's because we want you to do the best you can come July next year. So make sure you do some revision, make sure you go back over Unit 4. When we come back, we'll start the next module, and you'll see just how lovely this course is.